steady state device efficiency. So I've kind of strung you along a lot to show you why we're doing what we're doing, because we're going to characterize devices specifically and understand how they operate and how they work. So again, to discuss a turbine is this big device with blades that gives us work. You're gonna have some gas going through it. You're gonna let the gas expand through it, and as it is expanding through it, it's going to move blades, which are hooked to some rod, and the rod can do whatever you want out of it. So those are big turbines. There's the size of hangars, often, and sometimes they're tiny. But these when we talk about turbines. You could use that for a variety of different ways, and they're used in engines, etc. So our goal for a turbine, of course, is to maximize how much work we get out of it. Okay, so when I'm showing you the relation here, we're going to assume we're going to have one gas going in and the same gas going out. We're going to assume it's a steady state process, meaning we let it go for a while before we started doing any measurements. We're going to assume that there's no change in potential and kinetic energy, and we're going to assume it's adiabatic. Valid. These are all valid ways to look at it. Those are usually the way we design turbines. And usually you want to look at a turbine at steady state. Steady state is not really an ideal system. It's let's wait a bit and see what happens. Okay. And I haven't discussed this before, but when you go to the lab or when you go and design something for steady state, how do you know when you achieve steady state? And you may have an instructor yelling at you saying, how do you know you achieve steady state? And I've had that before when I was teaching senior lab. And people said to me, I don't know, after 5 minutes. Oh, I don't know, 15 minutes from now. And I go, well, how do you know 15 minutes? I know it's 5 minutes. You don't know. There's no set time for steady state. What you do is you put maybe a thermometer in it or a barometer in it or whatever you want. And you look at it, the output of your measurement. And when your measurement is constant with time, that's when steady state occurs, or approximately constant with time, of course. You're not going to, if it's going to change a little bit, but you're going to wait for the fluctuations to kind of stabilize. And that's when you can impose the steady state assumption. And that's true for a flow through a turbine, using a compressor, using a pump, using whatever you want. That is true. Anyway, going back to the first law of thermodynamics, open systems, you will get that work is equal to the negative change in enthalpy. And if we define the adiabatic efficiency for a turbine as the actual work divided by the isentropic work, okay? So the numerator is what you're actually getting out of the turbine, and the denominator is what you could potentially, if everything was perfect and the universe was awesome, get out of the turbine. All right, so the denominator is not achievable, but the numerator indeed is. So what we could see is from the relation from the first law, since I want the work, I'm characterizing the turbine in terms of work, I can now replace, using the first law, work with enthalpy. And so I can define the efficiency of a turbine as the ratio of the enthalpy change, the actual enthalpy change divided by the isentropic enthalpy change. And so if you look at it in a diagram, you can kind of understand what's going on. This is why we use the Mollier diagrams. You have HS diagrams. You have the enthalpy in the y-axis. You have the entropy in the x-axis. And if you look at the light green, which is the vertical arrow, that is an isentropic process because S is not changing. And the dark green is your actual process. What you're going to do is you say, my starting conditions are the same. And so you could see that for a real process, quote unquote, okay, your pressure is going to be, your P2 is going to be different from that of your isentropic process. And you can use that to understand the efficiency of a turbine. So let's look at specifically a hydraulic turbine. I think you can kind of appreciate it that way. So for a hydraulic turbine, you know that delta H is equal to this. And since it's hydraulic, meaning that it's got water in it, meaning it's incompressible, the delta V goes away. And so I get this. So the numerator is the C delta T plus V delta P, and the denominator is V delta P. Okay, so what does it mean? That for an isentropic process, we already know delta T is equal to 0, so that's why the denominator doesn't have that C delta T stuff. Okay, we also know, okay, that if we look at the second law of thermodynamics, okay, for this particular system, for steady state, under steady state assumption, we can show then that delta S is equal to m dot ln of T2 over T1. Since this thing is adiabatic because isentropic, that means that the entropy generation is equal to delta S, and that means that the entropy generation is proportional to ln of T2 over T1, which means that the only way for this to occur is when T2 must be bigger than T1, because otherwise it would make the entropy generation term negative, which is impossible. So delta T has got to be greater than 0. And for a turbine, delta P has got to be less than 0. That's what we're trying to do. We're trying to make the delta P as low as possible. So for the isentropic process, delta P will be as low as possible. And for a real process, delta T is going to mess it up. And delta T will be temperature, will be your measurement, your tool, and your metric to understand the irreversibilities within a pump, within a turbine, I'm sorry. Okay, the higher the delta T, the more irreversibilities you have in your turbine. And so that you could think of it as a way, well, why is the temperature increasing? Maybe because of friction, maybe because of other types of dissipative effects within your turbine. And so maybe you got to clean it up, or maybe you got to replace some parts, etc. But T is a really good measure to understand your performance against an idealized performance, which you can evaluate directly here. So when you can look at it directly here as well. Again, over here, you can also see we're trying to minimize delta P. That's the idea. And so you're always going to have a more minimal delta P for an isentropic process than you would for a real actual process. Okay, let's look at a nozzle. And again, a nozzle is this thing that's trying to increase the speed of a fluid at the expense of pressure. And so let's show how that works. So since you're trying to increase the speed, that's what you want out of a nozzle. You're trying to constrict the area and get the speed up. We're going to define the efficiency, the entropic efficiency of a nozzle using velocity. So we can say that in the numerator, we're always going to have a lower value than in the denominator. All these efficiencies only go from 0 over to 1. So I'm going to have the highest possible velocity when I have an isentropic process, like at the bottom, like with the 2s, s standing for isentropic. And I'm just going to impose that we start at the same velocity, whether we're doing it isentropically or we're doing it for real. Okay. So from the first law, if we're assuming adiabatic, one inlet, one outlet, no potential energy, no work, then we get that delta H is equal to the change in kinetic energy. So if the change in kinetic energy is directly equal to delta H, I can replace delta KE with delta H. So I'm getting pretty much the same thing. And I can use the same diagram now to look and understand how to get the most efficient path that's as close as possible to an isentrope using the Mollier diagram. That's what we have all this stuff. So again, for a real process, Vel2 will always be lower than the isentropic Vel2. That's the highest possibility you can have for it. Okay, so again, it's the same exact picture as before, and we're going to start with the same pressure. You can start with the same velocity. Okay, let's look at a hydraulic nozzle. Pretty obvious kind of thing to do because you're going to usually use a liquid in a nozzle. So in that case, we've shown already that delta H, as we did over here, delta H at the denominator here, see, delta H under an isentropic assumption is V delta P. So we're going to put that here as well. We have V delta P in the denominator, and in the numerator, we have the velocity, which we're trying to maximize. Okay, so what happens is we have two possibilities here. for a nozzle, I can maintain the pressure constant. Okay, if the pressure drop is constant, okay, that must mean that my velocity for my isentropic process has to be higher than that in the actual, and therefore the area for my isentropic process has to be higher than my actual area. I'll always get a larger area or a larger velocity. If I'm fixing the geometry, I'm saying the area won't change, the velocity won't change. I'm fixing the output velocity. Then the only way for this to occur is if delta P changes. So for an isentropic process, okay, my delta P will always be lower than in an actual process. Very similar to what we've seen before. Okay, let's look at a compressor. A compressor is a device that you're going to use to increase the pressure of a fluid by reducing its volume. And when you do that, you need to put work into it. So now this one and the following device are kind of flipping it. The isentropic stuff goes in the numerator. Why? Because it's going to be lower. We're trying to minimize the work we're putting into this stuff. I know the compressor costs me money. I have to put work into it. So if I need to do work for it, okay, then I'm trying to minimize that. Then the lowest possible work I will need to run it is when it's isentropic, when it's reversible, when everything is at equilibrium, when there's no driving force, when everything is la-di-da and no dissipation to the surroundings. So again, I'm going to put the work in the top and I'm going to put the work in the bottom. It's isentropic at the top of this case instead of the bottom. Since we're assuming there's no heat, there's no KE and no PE, work is necessarily delta H. So we have, again, delta H versus delta H, except in this case, we're coming from the bottom rather than the top because, well, we kind of flipped it. So we're going to start at two different pressures, but we're going to end at the same pressure. That's the idea. We're going to maintain the end pressure to be the same. My goal is to reach P2. I don't care how, but my goal is to reach P2. That I know that for an isentropic process, I will then have to start at a lower P1, at a lower value over there for the P1, whereas for a real process, I will have to change it. So that's kind of how that would work. All right, let's look at pumps. Pumps are very similar to a compressor. And so this idea is to try to increase the pressure of an incompressible fluid. So over here, I'm doing it to a compressible fluid, and here I'm doing it to an incompressible fluid. So in this case, a liquid. So this is for gases, this is for liquids. Same idea. I get the exact same idea, except since this is hydraulic or incompressible fluid, I can replace these terms directly with V delta P, and I can maintain the work at the bottom to be the same. So what I'm seeing is that if I'm maintaining the work between the two processes to be the same, then the change in pressure for an isentropic process must be higher. But if I maintain the pressure to the delta P to be constant, then the amount of work I have to put into my actual process will always be higher than that for the isentropic.